We continue our series on sheet piles walls with anchored sheet pile walls. The difference between an anchored sheet pile wall and a cantilever sheet pile wall is very simple. It includes an anchor or a tieback of some kind added near the head of the wall, and tieback can take a number of different forms. More than one set of anchors or tiebacks can be used. It increases the wall stability, enable taller walls to be built and sustained. And for permanent works, it's just about a must. And for also lighter sheeting, such as aluminum, vinyl, and fiberglass, it's also a must. They're used with all types of systems. Tying back walls is very, very common in retaining walls. There are many ways of tying them back. The common, and I talked about these, are either unpiled deadmans or piled deadmans. They call it cap and a deadman, but really, either the deadman simply operates again, the wall pulls it this way, the deadman resists through passive pressure along the surface. And so that's easy enough for that. You have the same concept with a sheet pile anchor. This kind of is a segue into something I don't spend a lot of time on in anchored walls, and that, of course, is king pile systems, where sometimes you even have a sheet, a very sophisticated anchoring system on the backside where you have long piles driven for that. I don't spend a lot of time in that in this course. I do spend a considerable amount of time in sheet pile design by pile block on the issue. Of course, so you can support these using pilings. Again, in most cases, this is a tie rod with a nice turnbuckle to tighten things up. I talked about H piles, and they're grouted. Again, any kind of grouted, whether it's any kind of grouted tieback for a sheet pile wall requires a competent sole, or even better, rock. And many times in marine applications, you don't have that, but in other applications, yes, very much. If you've got rock or competent sole, grouted tiebacks are the way to go. And last but not least is sheet pile anchors, and there's a couple of forms of those, and I mentioned those earlier. The biggest and most important is that every tieback system just about uses wales. Wales are simply, we've got the sheeting, which is vertical. A wale is a horizontal beam. Usually it's an H beam. It doesn't have to be. Many times with wood, you've got these large rectangular wood sections. And the idea is that the basic problem is this. With any tie rod system, as opposed to like an MSC wall where you've got continuous or somewhat continuous connection between the wall and the wall behind it, tie rods are an intermittent connection. And therefore, the load has to be transferred from the tie rod through the wale and to the sheet pile wall. And basically, the wales act as a beam simply supported at each point in the tie rod. And you basically have, and then you have, we normally assume, uniform, the soil presses against the sheeting. That in turn transfers a uniform load to the wale, and then from the wale to the tie rods. Wales can either be inside the sheeting if their protrusion is a problem. If you can put the wale outside of the sheeting and simply tie off to the wale out here, that's because everything then is in, this is in tension, but this connection from here to here is compression. There's obviously compression. It's much better if you can put the wale on the outside and tie it off that way, as opposed to putting the wale on the inside, tying it off, and then have a tension connection between the wale and the sheeting. But you see both. Generally speaking, you put the wale on the, generally it's on the outside. Another thing down here is that some of your, I'll go back a slide just to make sure I'm clear. Many times with straight up tie rod, they're basically horizontal. With not all, but they don't have to be. If you've got a situation, for example, where you've got a sloping, competent soil, you have to, in order for this thing to work, you have to do two things, at least one or two things. First, you have to get this past, or at least as far as possible past, the failure envelope, where, say, down here at the bottom of the wall, you have a failure envelope that's flat, like we had with MSC walls. It's the same concept we had with MSC walls. You have to this has to be beyond this failure surface right here in order for it to work. Sometimes you can edge it up close to it, and it gets. In fact, if you look at, for example, DM7 mentions that not only you've got this failure envelope to get past, but you have this failure envelope to get past. And in fact, DM7 tries the ideal situation is if you get this past this up to the surface and then down is ideal. We'll see that here in just a little bit. That's important. If you need to get past that, and if you can get away with it, get back to a competent. So if you got something competent coming up here, then you would be wise to get into that. Well, the thing is, with those, is usually with an existing stratigraphy, it's usually upsloping like this to competent whatever, be it soil or rock. And so you will angle to get to that, you will angle the tie rod down. Well, the problem with that is that you end up with a horizontal and a vertical component. Well, the vertical component you're stuck with. If almost all sheet pile walls are vertical, therefore the tieback loads are going to be horizontal. And when you do this, you create vertical loads on this. Now, for the sheeting, that's usually not a big deal. But for the tie rod's load actually increases. Because if you take this force triangle to this, obviously this is going to be larger than this, which is what you're designing against. Okay, that's the quick and dirty overview of anchored walls and how they're held in place. Design methods. They are an extension of cantilever walls, or if you want to look at it the other way, cantilever walls are a simplification of anchored walls. If we go back, maybe I'll just use this down. Well, maybe I won't. Maybe I'll go to the next one to use it for my. I had one anchor here. Up to this point is here. I have at an anchor with an anchor load T on it. And the goal, once again, is to determine how deep this D is going to be. And then from there, I can compute my moments and internal stability and all that good stuff. The question is, how do I do D? There are, I have, in cantilever walls, and one thing that freaks people out about sheet pile walls who are used to nice beam problems and mechanics of materials and statics and all that good stuff, is there's no support, visible means of support. You just have two forces acting against each other. So how do I do supports? Well, I know one support I've got, and it is at the anchor. That's basically a simple support of the tie rod. It can go this way and that kind of thing. We assume it to be a simple support for statics purposes. There's some moment resistance needs to be there, but usually it's simple support. It can be designed as simple support. And so there's several ways of dealing with it. One of them, and the problem is the bottom. The bottom of the sheet pile wall is obviously here, the toe of it. How is it fixed? Well, it depends a lot on what method you're using. First of all, Whoops, I'm getting a little bit of a lag here, so don't worry about that. Free earth support method. It assumes that the lower end of the pile is incapable of producing negative bending moments, and it converts the problem into a statically determinate one. Now, it's the simplest. It is the most common method of doing it. It is the method that SPW 2006 uses. And the hitch with it, and we're going to talk about this in a minute, is if you use a classic type of solution, then the bending moments you see in the sheeting are unrealistically high. And we're going to get into that in just a minute. We in Rowe's moment reduction method and all that. With a soil structure solution like 2006, in my opinion, now I could be, I'll assume have people dispute that, and they have good reasons to dispute it. I don't think Rowe's moment reduction is necessary if you've got SSI and it's set up properly. And that's always the big if with SSI methods, is setting them up properly. A fixed earth method is Blum's method. It goes back to an individual named Hermann Blum who developed it in Germany in the 1920s. Basically, he picks a different lower end condition. The lower end condition has no angle. In other words, if you remember from beam theory, you start out with shear, integrates to moment, integrates to angle, integrates to deflection. We assume no angle. In other words, that the sheeting is perfectly vertical at the toe, but it has no moment there. Now, it results in a sheeting which is longer, but has lower moment. Now, Blum's method, there's always been this this is another one of those little things we get into sheeting where you can't really agree on anything, but Blum's method is is good in certain situations. Let's put it that way. In my opinion, I think that with free end versus fixed end is not as much a difference in the underlying concept. It is a little bit different design objectives. The toe, changing the toe conditions is a different design objective in whereas Blum's method wants a fairly stable, it is more towards a stable sheet. There are a couple of advantages. The advantage of that is it's a lighter sheet, but the disadvantage is it's a deeper sheet. Whereas with a fixed end moment, you tend to get a heavier sheet, but the penetration is less. So, and which one you want depends on a lot of things. There are certain types of sheeting, such as, particularly with vinyl and fiberglass, where I would gravitate towards using Blum's method or fixed end before I would do free end. Most steel sheeting is designed using free end. With Blum's method, I think fixed end is the better. And it does not require Rowe's moment reduction in that, and it is definitely more conservative in terms of the penetration. There's also beams and elastic foundations with plasticity, which is kind of what you see in SPW 2006. All the methods can be, in terms of implementations, the list that I reeled off in cantilever methods are the same. Their anchored walls are both simpler and more complex. The key to the solution of anchored walls is to take the moment around the anchor point. And if you do that, then the anchor point no longer becomes an issue in the balance between the active side and the passive side. And then you can design for your overturning that way. Blum's method, I'm not going to spend Verreut spends some time on the theory. I have a much more involved blow-by-blow technique that we use that discusses the development of Blum's theory and how people have tried to make it simpler to implement. Blum's theory is another one of those things where the theory was developed before the computing power really caught up with it. And I have a simplified implementation of Blum's method that eliminates a lot of the assumptions that people have had to use to simplify the computations. And you will have an opportunity to use it if you're interested in this. I have a monograph on the subject. The monograph is fairly popular since I put it on ResearchGate a couple of years ago, maybe. It's done quite well for itself. So it's a subject that has a great deal of interest. So you will get a chance to use the implementation of that for very simple cases, and we will avoid some of the complexities that Verreut and other people get into with it. Let's take an example, a simple example. This is the same example we did with cantilever walls, only this time we're going to do it with an anchored wall. We're going to add an anchor. We add one additional variable, and that is A prime, which is equal to A, the distance from the top of the wall to the anchor location, over this H. That's the only thing we're going to add. All the other variables are the same. Everything else is the same. And we take the moments around that anchor point, as I pointed out just a few seconds ago. What we get is complicated. This is the simplest case. There are 4 equations that I'm going to deal with, and I actually use those, actually color code and number code them. There is a reason for this, just to keep everything simple. So I would suggest that you can save yourself a lot of trouble by using these charts. And I think I have them. They should be on the website in spreadsheet form as well. First, anchored wall penetration distance equation. If I go through all the math and I do the moment around the anchor point, I end up with this equation. Now, this equation needs to be solved. It's a function of A prime, which is a given. At least I assume an A prime. I mean, once I get this thing solved, I may decide I don't like the A prime, but we assume it. A prime is also constrained sometimes by the geometry of the job or whatever. Kappa, which is of course the soil, and that's where you take your KP over KA, and the KP is you should reduce the KP by a factor of safety or whatever. So therefore, the only variable is D prime. Now this is a nice cubic equation, and it can be solved in closed form. To generate the tables that I didn't solve it in closed form. I used Newton's method to solve it. I think Verreut pretty much uses a numerical method as well. So we don't use closed form methods for that. It can be done, but it's not very practical. Numerical methods generally give a lot more reliable results, and Newton methods works extremely well with this. I mean, it's differentiable, and if you pick a night, it's easy to pick the starting point well, and then you just go for it. The second is the anchor pole ratio to active. Now, I was tempted to, normally speaking, in American practice and the charts that we use, we multiply both sides by this denominator term right here. And we get T over Ka gamma H squared on this side I stuck with Verreut's just for your benefit and for consistency. If it was up to me, I would multiply this out and be done with it. It makes the math a little simpler, and it's more in line with the charts that we've used over the years in stuff like Sheet Pile Design by Tieback and the USS Sheet Pile Design Manual. The third equation, number 3, is the location of the maximum moment, which we obviously need to know to find out what the maximum moment is. It's derived in the same way we did with the cantilever walls. And last but not least, the dimensionless maximum moment, which is now this is the same ratio I use in the charts in Sheet Pile Design by Tieback, and I think that came from DM7. M max over Ka gamma Z cubed is equal to this expression. Now, that's a lot of algebra. So what I did was I have tables. This is for equation 1. This is the left hand, this is the solve for D prime. We solve this for D prime. All these are D prime solutions. And you see that, and there are 2 variables here. One is kappa. And kappa, I use the same range that Voigt did for kappa. I've kind of tried to stick with Voigt's scheme on this in terms of the values of kappa. And down here is A over H is down this side, or A prime. A prime is this way, and that's true for all 4 charts are done that way. All 4 of them. Alpha is A prime is this for any given A prime, and kappa, D prime is in here somewhere. That's the first one. The second one is the same. It's the left-hand side of equation 2. It's this right here, and it's given, and that's the anchor pull. If you know, once you've computed D prime, you can use the value from this in the other 3. So again, so therefore, these all imply this as the other 2. All 4 of these imply that we know D prime. That D prime is determined for any given values of A prime and kappa. I know D prime, therefore if I know this, I can compute that. Pick any of the corresponding ones. So this is the anchor pull dimensionless variable, number 2. Number 3 is the location variable. This is basically the Z over H for any Z over H or for the maximum location of the maximum moment. You will note that all of these variables are less than unity, and what that means is that the maximum moment generally takes place for anchored walls above the dredge. And of course, I only go down to A over H, or A prime is equal to 0.5. In other words, I assume that the lowest that you would put an anchor is halfway down the wall to the dredge line. It is obviously possible to do more than that, and we'll talk about what that means here in a minute, what that distance means. It's generally not done unless you're doing more than one of them. And last but not least, the moment equation, the dimensionless moment equation, which I can use that to compute the maximum moment. So let's take the same example, and all I'm going to do is add an anchor point, 2.5. Now I'm assuming again that the anchor point is the anchor point is a simple support for this. Ratios from the equation. Instead, you can look these up. A prime is 0.25, and you get kappa from the previous example, and everything else from the previous example. Since we know A prime and kappa, we can compute D prime is 0.516, which means that the penetration is a little over a half. The anchor pull ratio is 0.305. The Z prime for maximum moment is 0.837, and the moment ratio is 0.108. By the way, the anchor, once you get your values of how do I derive the anchor point? Just as this is important, actually. Let me back up for a second and a couple of slides and explain. I've got opposing forces. In other words, I have this all resolves into a force, and this all resolves into a force. And one or two of you have probably by now thought to yourself, well, we talked about beating to our heads about sliding and overturning every other wall. Why is, suddenly, then we talk about taking a moment from the anchored point, which implies an overturning. Why doesn't he talk about sliding? With anchored walls, the whole concept behind this is to basically balance the sliding force. So basically what we do is that the active forces, which go this way, are equal to the passive forces, which go this way, plus the anchor pole. That's how I get that. That's how that is derived, just for your information. And that prevents sliding. Again, I take those, this shows you, and this is important because if you get a problem along these lines, you need to be able to solve. All I do is I take those dimensionless ratios and I multiply the anchor pole ratio, and I essentially solve for the real value. So in the first case, D is pretty simple. You take D prime times H, you get 5.16 feet. The second one, the anchor pole ratio, I take the ratio, I multiply it by the denominator on the left-hand side of equation 2. I get that. Z is pretty simple. I take Z prime times H, I get in thirds, 8.37 feet. And last but not least, the moment ratio, I take the maximum moment, I take the moment ratio, multiply it by the denominator on the left-hand side of equation 4. I get that. That's it for this equation. The math is you see that the math is messy, even in a simple case. And it doesn't get any easier when you start complicating things, which is a big reason why I recommend I know that we transition into using software. And this is, SPW 911's sheet pile solution to this. And you'll see the results are pretty much on par with those of the closed form solution. You'll notice that, and one of the nice things about this is it gives you a graphical representation. It shows you for example, this is the moment. The red line is your moment. And you see the moment is about right here where you would expect it, where we computed. This is the shear. The shear comes out here. It makes a big discontinuity. And then it comes around here to there. And then this is the net soil pressure. It increases up to the dredge line and then it comes back. Free earth analysis of anchored walls is traditionally a very complicated process, and this comes from DM7, published back in the days when hand solutions were or graphical solutions about all you had. So this is the concept. If you start adding things like unbalanced hydrostatic pressures, layered soils, cohesion, things get messy in a hurry. And this gives you actually an example of that. One more thing I want to discuss with anchored sheet pile walls using free earth design methods is Rose moment reduction. And Rose moment reduction was based upon the research by a British researcher named Rowe in the early 1950s, who actually did some model tests on sheet pile walls. And basically what he determined was that the moments that sheet pile actually were experiencing, anchored sheet pile walls were experiencing, were too high as calculated and lower in practice. And the basic reason why that was so was because the point of contraflexure in the sheeting was being raised by the actual interaction of the sheeting and the sole. Now, the point of contraflexure, maybe I ought to go back a couple of slides. The point of contraflexure, normally sheeting starts this and then it is the basic point at which the sheeting's curvature changes direction. It's generally below the dredge line. And with that, with the actual interaction of the soil and the sheeting, that point of contraflexure was higher than what was being predicted using classical methods. Classical methods assume that you either have a fully active or a fully passive condition along the sheeting wall. There's no interaction between the sheeting and the soil considered in classical methods. And the fact of the matter is that many sheet pile walls even now are designed using classical methods. And so Rose was able through his model test to come up with the fact that the maximum moment was reduced under certain conditions, and this chart here shows that reduction. It was done on model test on steel sheeting. It has not been, I don't know if there have been full-scale tests on this or not, and I really don't know if they've ever used it for non-ferrous sheeting. Of course, if you use free earth support, you don't need to worry about it. Nevertheless, it's an interesting result of. It was really kind of the first time that in the interaction between soil and sheet piling is a fairly flexible. Is fairly flexible, and that being the case, as it interacts with the soil being an elastic plastic medium at least, and more complex than that in reality, the interaction between a relatively flexible sheeting and flexible soil basically will produce results that will differ from those which are nice, neat theory sometimes predicted. And that worked in people's favor as they were designing sheet pile walls, but it produced excessively conservative walls. So Rose moment reduction was an attempt to get at that problem. Let's take an example. This example came from the British sheet pile manual of an anchored wall, and it shows you it shows you low water and high water example, weep holes, to make sure that this water gets down here and doesn't get too high. A tie rod, it's a 7 meter H and a 1 meter A, and we want to obviously know what D is, and it assumes 3 meters. Obviously, the object of this is to find out what that is. And it gives you more detail for the hand solution, which was at one time the way we did it. But we're going to tackle problems like this using the sheet pile software. Now, I have a complete tutorial on the subject. 3-part tutorial on how to use this software. And I think I can even go into using this example. You need to look at that before you start playing around with software. The software is easily installed. I even have a piece somewhere on how to do it on a Mac or Linux. And all I'm going to do here is I'm going to hit a few highlights of the software. You need to read the tutorial. I may even produce a video tutorial where I actually do a screenshot type of thing, where actually I show you on the screen how this thing works. In the meanwhile, however, there are a few things I want to note about SPW 2006. The first is the active-passive stroke on this thing. SPW 2006 has soil structure interaction in it. And basically what it assumes is that the soil, for large deflections, for example, on the KA side, has flat, and then it has it linearly goes up through the neutral point here, the K naught here, and then goes up to passive, then it flattens out again. That's kind of a similar type of simplification that we use when we use elastic purely plastic. It requires you to figure out what that stroke is. And what I mean by the stroke is the distance between the neutral point and the point at which you achieve either full active or full passive. The way you do that for our purposes, and there are other ways of doing this, but for our purposes, just to get started, we're going to use this chart, which is in your textbook. I think they got it from a Canadian Foundation Engineering Manual is where they got it from. They have a situation where you have wall rotation here and H here. We know what H is. And the maximum wall rotation is equal to H times one of these factors. And these factors depend on what dense cohesionless, loose cohesionless, stiff cohesive, and soft cohesive. That's pretty general, but it'll get us started. And then you multiply H times that, and you get the stroke. And the stroke is input. Let's go ahead and get over here when you're putting in the layering for this. Your stroke is over here, and this dW is the stroke. And I'll explain why it's only applicable to one layer. The stroke should be no greater than that. Obviously, the smaller the stroke you have, the more that you come to classical sheet piling methods. Because the classical sheet pile methods basically assume the stroke is 0. So you can use that. It's possible to, on the passive side, to use, down in the lower regions, to use a stroke which is based upon an estimated D. If you have an estimated D, you can use, instead of Y over H, you can use Y over D for that, if you have a decent estimate of D going in. Otherwise, use the other one. Okay, now I want to make a few comments about this program. Like I said, I have a much more detailed tutorial, but I want to make this is the chart it gives you. Basically, SPW 911, and I think a lot of your newer sheeting software is going this way, assumes a staged excavation approach to sheeting design. And what I mean by that is that it assumes basically that sheeting starts out with the same on both sides, and then you basically dig this down. So therefore, you'll see that loading step 1. Well, loading step 0 is your basic soil setup, and you basically do your setup in loading step 0, which is the same on both sides. Well, it's not really. The layering can be the same on both sides, but not necessarily some of the variables therein. But it's easiest. The easiest way to set this thing up for our problems is to set it up with the layering the same on both sides, the variable same on both sides, and then basically dig down. When you go to then you create step 1, and when you create step 1, you create this. Like the left side of this is this layering, and what I did basically this right side here is the same as it is. The right side has the same layering on both, and in other words, both of them start with the right side layering. Left and right are the same in step 0. This is what step 0 looks like. And then to get to step 1, all I have to do is to set the WD to 0 for all the layers that I excavate. In this case, there's 1, 2, 3, 4, 5 layers. I just set 0 for the first 4, and that's it. The program takes care of everything. That's the easiest way to get set up in this. That's the first thing. Second recommendation, that little diagram over there is there for a purpose. Use it. Don't just throw a bunch of numbers into this thing and hope for the best. Don't do that with any computer program, but not with this one either. The program, so you need to, every time you make changes here, you need to look at what you're getting. Third, the anchor. This program will analyze both anchored and cantilever walls. It comes initially with an anchor. If you use it for a cantilever wall, you need to get rid of the anchor. But over here is the menu for the anchor, and there's only one anchor, and the anchor point also has to be a layer boundary. Even if the soil doesn't change, you have to put a layer boundary there. You will note that anchor has an FA of 500 and a DW of 0.02. Basically, the DW it assumes that the anchor is an elastic, purely plastic. In other words, it will basically stretch until it hits the maximum FA, and then it just extends like taffy. If you want to be proper about it, I would, for our problem, obviously, the yield, obviously in a real problem, what you would do is you would compute the yield, you would check the yield strength of the steel. You would multiply that yield strength, or your allowable, let's put your allowable, times the cross-sectional area. Once you get, that would be your FA. And then you would take that and you would basically use delta is equal to FL over EA to determine the DW, and you enter it as a negative number over there. That's the proper way of doing it. You can also, if you don't want, for our problems, we're not going to worry too much about plastic deformation of the anchor. Now in a design project, that's different. But for our problems, we won't worry too much about the design of the anchor. If you can do it based upon, if you give some idea how long the anchor is and how its diameter, you can basically set any allowable stress you want and then compute the F, and then FL over EA gives you your delta, and you're done. Set any force you want, and then you multiply length divided by EA, and you're done. That's, if you want to avoid, it's better to have a more rigid anchor than it is too flexible one. Too flexible of an anchor will give you some very strange results, which can be violently non-conservative. So I would definitely tend towards a stiff anchor for both for class problems and for real problems as well, until you get a good amount of experience in it. Again, actual commercial sheet piling software is going to have a more is a fancier way of implementing this, and it should. In fact, some of them will even give you dead man design, which is really nice. And I also suspect that the flexibility of the anchor is another reason why sometimes the results that we get, that some experiments don't always match. The flexibility of the anchor is an important aspect which we frequently neglect in sheet pile design. You get, in the end, maximum, you get several things. First, this is the deflection. Then the moment. Then the shear. You notice this big shear discontinuity. And then you get this, which is kind of scraggly looking. You wouldn't normally expect this. Now, this is more or less according to expectation, but some of this isn't. Some of it's due to the presence of unbalanced hydrostatic forces and all that, but some of it's also due to the soil structure interaction, which redistributes the stresses of the soil. Like I said, I have a complete explanation of this and some of the other quirks of the software. I may be able to prepare a video presentation of this later, but for the moment, this is a quick overview of it. You need to go blow by blow on the tutorial to learn how it's done. And I have a nice summary of this. One interesting twist, there are a few interesting twists. One of them is the software, for reasons I don't fully understand, Vroit reports the stiffness of the, instead of letting you give E and then give I, tells you to give the modular elasticity E and then the product of the modular elasticity and the moment of inertia EI. That doesn't, that's probably it's fairly confusing. All of that is, if you use the database that is given in the software, all that is taken care of for you. The tricky part is when it meets structural requirements. And I've got this nice little outline over here which gives you the blow-by-blow for that. So you need to follow that. In fact, that's what all of this is for, is estimation of the maximum moment. Not just the maximum moment, but once you get the maximum moment, whether the maximum stress, that maximum, is acceptable. And if you follow that outline, you should be in pretty good shape. The free earth support method is, and Vroit has a whole chapter on this subject, is assumed that the policy has no moment, the flexion end, but does have a reaction. The Vroit has a simplified method. I think mine is a lot easier to use. Some of my students in the past have just gone into Vroit without looking at mine. Mine's a lot simpler. In fact, I have an online implementation of that, and I may or may not do a tutorial on that, video tutorial on that. I do have some basic instructions on how to do that. Tiebacks and whales, how to design them. Tieback is a balancing act. You have the distance between them, S, as I show here. Obviously, what you want to do is to have the fewest tiebacks you need, but to get the job done. That's contradictory, though, because the fewer the tiebacks you have two problems. First, the fewer tiebacks you have, the more low per tieback you have, which is actually given in this formula right here. And you have the tieback stiffness, which is right here, which actually relates to the force, which is basically the force over that delta of the the force over the deflection over is the tieback spring stiffness, and that actually relates to what you have in SBW 2006. And the maximum moment in the whales between the two, they're simply supported. And last but not least, the maximum, the combined stiffness for wall tieback, which is actually what you're going for in 2006. 2006 does not returns your tieback loads in a kilonewton per meter of wall, or pounds or kips per foot of wall. It does not go into the fact that tiebacks are not continuous; they're spaced, and they divide the load up. I don't spend a lot of time on anchor design, and I probably should spend more than I do, but I don't. Just kind of was one of those things you kind of run out of time for. But basically, the object of anchor design is to get first to get the anchor outside of the failure zone. If you have an anchor within the failure zone, and this is the same problem we ran into in MSE walls with the friction with the LE portion. If you don't have, the anchor is not outside, then what will happen is when the wall fails, the anchor will just go with it. It won't really do anything for you. Whereas you want to get the anchor outside of that so that it will actually help to hold the wall in place when you have attempts at failure of the soil next to it. So these give you some guidance on that, on how to do anchored wall design. Another thing I mentioned this earlier about avoiding the problem of having the two zones of failure when they mix. If they mix, it basically degrades the anchor. Sometimes this is unavoidable. It's something you need to try to avoid. The ideal is that the two zones of failure do not intersect at all. Soldier beams are a cousin to sheet pile walls. Basically what they are is you have a series of H-beams which are either driven down the line, or in some cases they will actually drill and put the H-beam in, either in grout and or put concrete in it. They don't have to be driven necessarily. And then what you'll have is lagging. And lagging are basically pieces of either wood or concrete. I've seen both. Stacked up. The H-beams are just, as the name implies, H like this. And then the lagging uses that the inside of the H-beam as sort of a slot. They form two slots, and you just put the lagging down, the lagging rests in the two slots. They're very good in temporary structures. They're very useful. They can also be used tied back in permanently if necessary. They're easy to install. The design of them is very similar to sheeting. Probably the best treatment of the subject that I think it's the one I used in sheet piles done by Pilebuck is Caltrans's treatment of the subject. California Department of Transportation's manual gives you probably the best design for soldier beams. Well, that concludes the anchored walls. Until next time, thanks for watching, and God bless.